Now, so far, we've learned about different ways of classifying waves. Those included longitudinal versus transverse. We also said we can classify waves as pulse or continuous. And another word for continuous that we use for waves is periodic waves. And there's one final distinction or classification we can make. Before we write it down, let's take a look. Now, we are used to waves doing what you see on top here with red and blue. We're used to the crests moving across the medium. But what's happening in this case? Look at the green wave down below, and let me go to regular speed. The green wave down below has crests and troughs, but those crests and troughs are not moving across left or right through the medium. They're just staying in the same spot. The troughs turn into a crest, and then they turn back into a trough. So there is a cycle, but they're not actually moving across the way we're used to seeing. We call this kind of wave a standing wave, and it contrasts from what you saw on top. The red here is moving across. That's called a traveling wave or a progressive wave. These crests don't travel in green, so that's just a standing wave. Now, how do we create a standing wave? Well, to see, look above at what's going on with the red and the blue. We have two identical waves, right? These two waves are the exact same. One is moving to the right, the other is going in the opposite direction. And what's going on here is they're interfering with each other. So sometimes the waves overlap, right, so that they are perfectly one on top of the other, like right now. See how the waves are almost perfectly overlapped? And then other times, the waves are mirror images of each other. Let's watch and find a moment like that. Here we go. So this is pretty close to perfectly mirror images right there. And notice what happens to the green wave. Well, the green is just the resultant. When these two waves are mirror images, that's constructive or destructive? That's destructive interference, because the displacements are on opposite sides. Blue is negative displacement, red is positive at this location. So the green line is perfectly flat, because all of the crests and troughs are canceling out. So we're oscillating between this moment and this moment when the waves perfectly overlap. And when they perfectly overlap, that's constructive interference. So you have red plus blue, they're adding together to make this giant superwave. Now there's another interesting thing about standing waves. So look back at the resultant, the green down here. You see, watch my mouse. This one spot on the string, always reaches the maximum displacement. It goes really, really, really high and then really, really, really low. Right? So there are certain locations where the crests always appear, and those locations reach maximum displacement. We call these antinodes or antinodes. And then there are other locations, like watch my mouse now, right here. This spot, where my mouse is pointing, this spot never goes up or down. It's not moving at all. That's called a node. So we have antinodes is where the crests and troughs appear, where you go really high, really low. And we have nodes, which never move at all. So let's summarize what we've seen. We have progressing traveling waves, but the other classification you can have is a standing wave. Standing waves have a repeating cycle, and you could have just a single crest on your standing wave, or you could have a standing wave with like two crests. A crest and a trough rather. And we're going to start the cycle when no time has passed on the clock, so little t is 0. And we're going to end the cycle we're going to end the clock. We're going to stop timing when one full period, capital T, has passed. So after one full period, we are exactly back where we started. The shape has returned. After one full period, we have returned to how we started. So we're going to consider what the standing wave looks like half a period in, or half a cycle in, and then we'll also look at what it looks like, consider what it looks like a quarter cycle in, or a quarter of a period in, and then finally 3/4 of a period. Okay. Well, half a period in, what do you think? Remember that this thing is oscillating. It's going from a crest to a trough and then back up to a crest. So it's just oscillating up and down. So halfway into the cycle, it has gotten to the trough. It's inverted, or it's a mirror image of where it started. And likewise, for this one, this crest right here becomes a trough, and this trough here has inverted to a crest, like that. So that's what this standing wave looks like. Halfway in. Okay, how about a quarter of a way in? Well, we're going from this position down to this position. So from here to here, you have to pass through the center line when there is no displacement at all. So the shape looks like this, a quarter of the way in. And likewise, this crest is passing through the center position, and this trough is passing through the center position. So this is a perfectly flat line as well. By the same reasoning, down here for 3/4 of a period, at that moment in time, we have flipped. We're going from a trough to a crest, and so we have just now reached halfway. And likewise here. Alright. We said that there are these locations that are never displaced on a standing wave. Let's mark those. Well, first, those are called nodes. And it is really important for us to node this term. Be sure you node it. Okay. So let's mark the nodes. There's a node right here at the end and at this end, because those locations never change. Those positions on the string, they never go up, they never go down. So that continues on. What about this one? Well, there's a spot right here in the middle that never goes up or down. So this wave on the right has a node at the left, a node at the right edge, and there's another node at the middle that never gets displaced. So it has 3. The other term was for locations that reach the maximum displacement. You see that in your thinking crests and troughs. Maximum displacement. Crests and troughs are where we get maximum displacement. We called those locations on the string antinodes, or antinodes. So there are no uncle nodes, just antinodes. Okay. Let's mark the antinodes on these two strings. Here's a crest or a trough. That's an antinode. There's only one. How about over here? This is maximum displacement, so that's an antinode. And this is maximum displacement too. So that's a second antinode right there, at that spot. So there's 2 antinodes. Notice there's always an antinode between 2 nodes. Antinode between 2 nodes. Right. Now, we've said already above, on a string, when we tie the ends down, we make those ends fixed. We are defining them, or we're requiring them to be fixed ends. And if they are fixed ends, then are they going to be nodes or antinodes? Well, let's look. If this end is fixed, then it cannot move up or down. It has to stay in the same position, which means it has to be a node. And likewise for the other end of the string. So these fixed ends must be nodes. This is called a boundary condition, because at the boundary, at the edge, we have set the condition, there must be a node. So what's the condition? The condition is you must have a node. You could call it a boundary requirement too, but the term we use instead is boundary condition. And we're going to look at this in a moment, but this is important because when you have a finite length, right, like this, if you say there has to be a node right here, then certain waves won't fit. This wave won't fit. It won't meet the boundary condition because there's not a node where there has to be. We haven't put a node at the end. So by having these boundary conditions, we restrict which wavelengths will fit. This wave has a length that's just a little too big. Okay, so how is a standing wave produced? Well, that's what we saw in the video. The standing wave is actually the resultant. It's the resultant of two traveling waves. So let's say, here's how it's produced. Two identical traveling waves move in opposite directions in a medium. That's the first ideal, right? But those two identical waves, let's say comma, they're constantly interfering. And they produce a standing wave at certain wavelengths or frequencies. Remember, only certain wavelengths or frequencies because of the boundary conditions. So this is how a standing wave is produced. But what about nodes and antinodes? Well, let's look back to the video for a moment. We've got a node located right about here. Let's see, right here. So watch what happens at this location on the string, at this node. I'm going to slow this down. Let's go to 0.25. At this, here's the node, right here at this location, where my mouse is, you have red is negative, blue is positive. If we let some time pass, at this same location of my mouse, red is negative, blue is positive. Right here, still red is negative, blue is positive. And then they cross, and then now red is positive and blue is negative. And no matter how far forward in time I go, even if I stop here, at this location where my mouse is, at this node location, red is positive, blue is negative. So you always have destructive interference at the node. One wave is always positive, the other is always negative. So let's write that down. Nodes are locations where the two traveling waves always interfere destructively. And what about antinodes? Here's an antinode right here at this location on the string. Now you have to remember to keep watching. You have to keep watching where. You have to keep watching my mouse, this one location on the string. So you can't look over to other locations, just right here. And right now at this moment, red is positive and blue is positive displacement as well. If I let some time pass, red is still positive at this location, and blue is still positive at this antinode location. If I let more time pass, here they're just crossing the axis, so there's 0 plus 0. Now, we're letting negative displacement with red add with negative displacement of blue, and if we let more time pass, again still, right here at this antinode location where it's really, really far down, red has negative displacement, blue has negative displacement. And so no matter what moment we are in, no matter where we are in the cycle, at this antinode location, you are always adding the same direction displacement of the two waves. If red is negative, blue is too. If red is positive, so is blue. So this antinode location is a spot where we always have constructive interference. So let's write that down. Antinodes are locations where the two traveling waves always interfere constructively. The last thing is to answer this question. I've got a string with its ends right here and right here. Why won't this wave fit on the string? Answer that in your own words.